Okay, today we are going to talk about normal distribution, and with that, we're going to also talk about variance and standard deviation. So you might have heard of some of these terms before, but not really known what they mean. But to start out, variance and standard deviation, they are both different measures showing how much your data deviates from the mean or the average in your data set. And we use the little Greek letter sigma to represent them. So sigma by itself is the standard deviation, and sigma squared represents the variance. So you'll see these symbols quite a bit throughout our statistics unit, and we will be learning how to find those today. So finding your variance and standard deviation, first you're going to have to find the mean or your average of your values in your data set, and we use this little X bar, the bar over it, to represent that. So to find your mean, that's just going to be your average. So you would just add up all of your numbers and then divide by how many you have. So hopefully that's nothing new. And then what you're going to do from there is you're going to find the difference. So you're going to take each data number and subtract the average from it, or your mean. So say I have a data set, the point is 10 and my average is 9. I would do 10 subtract 9. And I'm going to repeat that process for every data point. So sometimes that can get kind of tedious when you're trying to do it for a large data set. Once you have the differences for each data point, you're going to take that difference and square it. So like on the example where I said I did 10 minus 9 would be 1, then I would do 1 squared and get that value. Once you have all those values, you're going to find the average of those. So this is the formula for it. It looks a lot messier than what it really is. It's mostly just tedious work. This is sigma capitalized. We've seen that before when we did our series unit back at the beginning of the year. That just means in math to find the sum of something. So it's saying you're going to take each data point and subtract the average from it, and then you're going to square that number, and then with that value you're going to take the average. So you're summing up all the differences, squaring it, and then find the average of it. And then to get the standard deviation, remember variance is sigma squared and the standard deviation is just sigma. So the difference between the two is this one's squared, this one isn't. So whatever you get for your variance, you're just going to square root that to get your standard deviation. So I know it looks a lot more messy. It really is more just tedious than anything. So before we move on to doing normal distribution, let's actually look at an example of finding this by hand. I'm going to pull this example up. So let's say I want to find the standard deviation. Again, the standard deviation is a measure of how spread out your numbers in your data set are. We use the little Greek letter sigma. And then for the formula, again, we're just going to walk through that process where we find the mean, then subtract each value, subtract the mean from it, and then square it, and then find the average again. So we have this little example with these dogs right here. It says you and your friends have just measured the heights of your dogs in millimeters. So here's your little puppies. The heights at the shoulders are all of these values. So 600, 470, 170, 430, and 300 millimeters. Find the mean, the variance, and the standard deviation. So again, the mean, we use the little X bar symbol. That's just your normal average. So I would just get my calculator out and we're going to just add up all of those numbers. 600 plus 470 plus 170 plus 430 plus 300. We get that total, and now we're dividing it by how many, and we had 5 dogs. So we're going to divide that by 5. And so that would be your mean, or your average. So our average dog height is 394 millimeters. So now we're going to find the variance. So variance, again, is your little sigma squared. So to do that, first we had to find the mean, and then now what we're doing is we're taking each data point, which are all of our heights, and we're going to take each of those and subtract the mean. So I'm going to do 600 subtract 394. I'm going to do 470 minus 394. So this is where, again, it gets tedious. 430 and 300. So let's go get all of those values. can't really see what I'm doing. So 600, if I minus 394, it's 206. And then repeat, 470 minus 394 is 76. 170 minus 394 gives us negative 224. And then 430 minus 394 is 36. And 300 minus 394 is a negative 94. So we get all those values. Then what you're going to do is you're going to square each of these values. So I'm going to do 206 and then square it. So our numbers will get kind of big here. And that equals 42,436. And then repeat, 76 squared. That equals 5,776. And then negative 224 squared. And then just a reminder, when you do negatives in your calculator and you're squaring it, you do have to put it in parentheses or your calculator will keep it negative when it should be positive. So just be careful. I have students make that mistake quite a bit still. So we get 50,176, 36 squared. So you can see why if you had a big data set, this would be really not fun to do by hand. I mean, this is only 5 numbers and it gets boring really quick. One more, negative 94 squared. So on these ones, we get 8,836. Okay, so then once you get these all calculated, now you're just finding the average again. So now we're going to find the average of all of these. So first you would just sum those all together. So if I add all of our numbers, and then we would just divide it by 5 again. So adding all of these together, plus 1296, plus 8836. Okay, so we got this as our total, 108,520. And then now we're going to divide that by 5 to get our average. And we get 21,704. Okay. So we just found the variance. Remember that sigma squared. So maybe I'll write that more clearly right here. So sigma squared is that 21,704. That's your variance. But then to find your standard deviation, that's just going to be the square root of that number. So if I take the square root of 21,704, we get a decimal. Let's just round to 2 places. Well, let's do 1 decimal, 147.3. And so that would be your standard deviation. So the standard deviation, here's your variance, and then our mean was up here. So those would be your 3 numbers. So it's definitely tedious to do it by hand, but I think it's good to see where the numbers come from, because again, really what you're seeing is the change between the actual data point and the average, how far apart they are. And the reason we square it is so that we don't have a negative distance, because what we're really looking for is how far apart are the heights from the average. And so this would be like a shorter dog versus an average dog. We got a negative number, but we just want to have the positive distance, so we square it, and that's why squaring will always give us a positive result. So that's how you find the standard deviation and the variance by hand. And the reason we like to do that has to do with the normal curve and the normal distribution. So with a normal distribution, you guys might have heard of like the normal curve before, or even seen pictures of it. You get this bell-shaped curve. So with a normal distribution, that means your data is distributed normally, and normal data is going to have the average be a little bit higher, and then on the lower ends you don't have as much data. So that's why we get kind of this bell curve. Most data is right here in the middle. This works with things like height. If we measured everyone's height in our class, it would be normally distributed, where most people are around an average height, and you might have a couple people that are really tall, a couple people that are really short. It would work with grades as well. Most people are going to be kind of here in the average C grade. You might have a few people that get A's, a few people that get F's. So with the normal curve, the little lines that you see here, here's your average right in the middle, your mean. These lines are deviations coming from your standard deviation that we just calculated. So in a normal curve, your data, 68% of it is going to fall between one standard deviation to the left and to the right. So from here to here, if I filled this in, this area covers 68% of my data from here to here. And then if I go 2 deviations to each side, this is now covering 95%. So 95% of my data is in between this point and this point on my curve. And if I go 3 standard deviations to each side, 3 to the left, 3 to the right, it now covers 99.7% of your data. So this is really helpful because so many things, if we did statistics with, would fall with a normal distribution like this, and we can use these percentages to find a lot of ideas or answers to questions. So since nearly all of your data, 99.7% of it, falls within 3 standard deviations to each side, we call this the empirical rule. And so when we are looking at our problems here, we can memorize these percentages to kind of help us with our problems. So again, 68% goes to 1 to each side, so that means in just this section would be 34 and 34. And just this little sliver is 13.5. Same with this sliver would be 13.5. And then between 2 and 3 on each side is only 2.35% of your data. Sometimes data is not normally distributed. In order to do that, it has to be a symmetrical bell shape. But sometimes you can get it skewed like these two. This one would be positively skewed. You see we have kind of a longer tail here on the right. And this one would be negatively skewed, where the tail is a little bit longer on the left side. So when a data set's skewed like this, they don't vary as predictable as a nice normal bell curve would. So the data, you can't interpret the percentages the same way. Because if I try to overlap these percentages, since it's not symmetrical, it doesn't work on that. So that's why we like having that normal bell shape so much. So we're going to look at some examples of how we actually use a normal curve. So example 1 is ACT scores. They are normally distributed, where most people get an average, and some people get really high and some people get really low. So on this first part, well, it says that 1 year, the mean score, let me zoom out a little bit, was 21 on the ACT, and it had a standard deviation of 5.2. So draw a normal distribution curve and label the means, standard deviations, and the scores. Okay, sorry, I had to pause the video really quick. So let's draw the normal distribution curve, and then we're going to label the mean, standard deviations, and scores. So we're just going to draw a little bell curve. Doesn't have to be anything fancy. But then the mean is going to go right down the middle. So they gave us that mean. They said it was a 21. And then now they want us to draw the standard deviations. So there's going to be 3 to the left. 1, 2, 3. And that third one kind of comes over by this tail. And then 1 to the right, 2 to the right, 3 to the right. So to actually label the standard deviations now, they told us the standard deviation is 5.2. You're just going to subtract it going to the left and add 5.2 going to the right. So 21 minus 5.2 is 15.8. If I minus another 5.2, it's 10.6. If I minus another 5.2, I get 5.4. And then now to the right side, we're just going to add it. So 21 plus 5.2 is going to be 26.2. If I add another 5.2, we get 31.4. And if I add another 5.2, we get 36.6, which you can't even get on the ACT, right? Highest is a 36. So that's all we had to do is find the mean, and this is your X bar. and then label your standard deviations. So if we talk about the percentages again, 68% of students would have fallen between a 15.8 and a 26.2 on the ACT. And then if we go one more to each side out, so now we're 2 to the left, 2 to the right, 95% of students will fall between a 10.6 and a 31.4, and then 99.7 would fall between a 5.4 and a 36.6. So they're saying, what is the interval that contains 95% of the scores? This is 2 deviations away on each side. So if I go 2 to the left is 10.6, and then 2 to the right is 31.4. So that would be our interval. So 95% of kids get between that. Okay, not all scores though are going to be exact standard deviations, right? Like, you can't get a 15.8 on your ACT, that's a decimal. So on something like this, where you actually want to maybe see what, if you put your score in, where you would fall, we would need to use a calculator to do that. So if you have your own graphing calculator, you can just follow along with me. If not, you can go, really, you could probably just Google a normal probability calculator, but here's one that you can go to. But you probably just search one on Google. And I'm going to show you how to do that. So what percentage of ACT scores is less than a 25.2? So if I want to know that, well, 25.2 doesn't fall right on my deviation, so I can't say, oh, it's 68% or whatever. 25.2 would be somewhere around right here. So if I want to see how much is less than that, that's where the calculator comes into play. So to do this, what you're going to do on your calculator is you're going to push the second button. Let me clear this out. So second, make sure you can see. And then this VARS button, if you look above in blue, it's short for distribution. We want this menu right here. And these different things come up. We want the second one, the normal CDF, stands for cumulative distribution function, and has these different menu items that come up. Sometimes your calculator won't give this screen. I'll show you what to do if that's the case. But if you do have this screen, you're going to type in your lower end, your upper end, your average, and your standard deviation. So since we're looking at anything, it said what percent of scores is less than a 25.2, that's 25.2 and under. The lowest we can get on that would be a 0, right? If you got everything wrong on the ACT, you would get a 0. So then the upper end, we're saying, is 25.2. They told us the average is 21, and then the standard deviation is 5.2. And then we're gonna paste it. So before I push enter, if you didn't have that last screen, this is what would come up. It would just come up in your calculator screen like this, normal CDF. You would have to type this part in. So you would do 0, 25.2, 21, 5.2. And then close your parentheses. So you would just have to type it in straight like that if your menu doesn't come up. So that if you just have a regular TI-84, that's what we'll do. If you have a TI-84 plus, it should have that menu pop up. Then you just push enter and you get this decimal right here. So if I have a 0.79, that means 79% of students have a 25.2 or less. 79%. So what that's saying is if I have my little normal curve right here, we know our average was 21, right? Let's say this was 25.2 right here. If I shade this part of my normal curve, that's 79% of my data is falling in that. So we're calculating from 0 up to 25.2. Okay. Let's try another one. Let's say we want to figure out what percentage of ACT scores is between a 28 and a 36. We're still going to do that normal CDF function. So again, you're going to go to second and then that VARS button, which will bring up the distribution menu, and go down to the second one, the normal CDF. And then this time we're going to just change the numbers a little bit. We're looking for between 28 and 36. So our lower end will be 28, our upper end is 36. Our average is still 21, our standard deviation is still 5.2, so we don't need to change that. So we'll paste it. Again, if your calculator doesn't have that screen, you'll just have to type these in, 28, 36, 21, 5.2. And just push enter, and we have this decimal. So about 8.7% of students. So not very many students fall into that area. Okay, and then what percentage is greater than 27? So we're looking at 27 and higher. So if we go into our normal CDF again, we're doing 27, and then the highest is 36. If you remember though, our normal curve went a little bit higher. You could do something higher even though, so like we say the upper's 40, you can't really get a 40 on the ACT. Technically the highest is a 36, but if you want, you could do a higher one. So enter that in and we get about 12.2 or 12%. So, and again, if we shaded our curve to kind of match that, let's say here's the 21, and let's say here's 27 on here, we're up in this little tail end. So we're saying that 12.2% of students fall in that area. Okay. Hopefully that makes sense. And there's one more thing I want to show you. That's what happens if they give you a percentage and they want to know the score. So in all the previous ones, they gave us a score and we wanted to find the percentage. We're kind of working backwards here. If they give us the percent, what score correlates with that? So like on this part, they're saying 70% of students scored lower than what? So like if I have a bell curve, they're saying here's 70% of my data. What is this data point? That's what we're trying to find. So what is the score that correlates with this spot right here? So we're kind of going backwards rather than having the score and finding this percentage. What we do on this one is called the inverse norm function. It's abbreviated inv norm on your calculator. It's gonna be in the same spot. You're still going to go to second distribution, but it's this third one down, the inverse normal. So how this works is it gives you an area, then the mean, and then your standard deviation. So the area is the percentage, but we're going to put it in as a decimal point. So 70 would be 0.70 as a decimal. And then our mean and standard deviation will still be the same. So 21 for our average, and then 5.2 for our standard deviation. So we just paste it. Again, if you don't have that menu, you'll type it in the parentheses like this. So 0.70, comma, 21, comma, 5.2. And then push enter and we get a 23.7. So we're saying that 70% of students scored below a 23.7 on the ACT. So we're kind of just working backwards on that. So let's do one more like that. So let's say, what is the range of the top 25%? So on this type of question, the inverse norm works on the lower end. So if you give an area, it gives everything to the left of that. But on this question, they're saying, what's the top 25%? So since the inverse norm here will give the left side of that, it's going to tell us the bottom 75%. When you need the top part, you're going to do 100% minus whatever the number they give you. So, because 100 minus 25% is 75%, right? So we're kind of working a little bit backwards there. So we're going to take still the inverse norm, and we're going to do for the 75% area, since this would correspond to the 75%, again, it always takes the lower half. So I'm putting in the 75%, the area and the average still stay the same. And I get 24.5 would be this point right here. So on the flip side though, now we're saying if I want the top 25, it's actually gonna go to the right. So 24.5 or higher. And really the highest you can get is a 36, right? So we're saying a 24.5 to a 36 on the ACT, that would be your range. And the top 25% of students score between that. So just kind of be careful when you're putting in the inverse norm at knowing that it calculates the left half of your curve, not the right half. So you have to kind of think of it a little bit backwards there. So I really like statistics and this kind of stuff because it is so applicable. Like you could literally go to any company or product and be able to do data with a normal curve. So lots and lots of applications for this kind of stuff. My husband literally does this for his job as an engineer all the time. So lots of cool stuff with statistics. Hopefully you guys kind of enjoy seeing how to do it a little bit. But if you have any questions, as always, feel free to email me. And then your homework is just on Math Excel. So go ahead and get started. See ya.